In this video, I will do a shift register experiment trying to illustrate how the 74LS164N 8-bit serial in parallel out shift register works. Arduino will be the development environment used. The target microcontroller board is Raspberry Pi Pico. DumbDisplay is used as I/O means for easy illustration. Let's get started. To enable Raspberry Pi Pico as development target for Arduino IDE, you will need to install Raspberry Pi Pico support. Go to Tool, Board Manager. Enter Pico into the search box of the dialog shown. Click Install button of the entry Arduino Embed OS RP2040 board. After installation, go to Tool, Board, Arduino Embed OS RP2040 board, and select Raspberry Pi Pico as the target development board. Make sure the correct port is selected. Now, you should be ready for Raspberry Pi Pico development using Arduino IDE. Since DumbDisplay is used, you will need to install the DumpDisplay Arduino library as well. Visit the DumbDisplay Arduino library GitHub repository. Click the green button and download the zip file of the library. Now, go back to Arduino IDE, go to Sketch, Include Library, Add Zip Library. With the File Select dialog shown, choose the zip file you just downloaded. You should now be all ready for the development of this experiment. Before seeing the connections and reviewing the sketch, let's see the end result first. The 8 LED in the gray triangular box represent the 8 bits of the shift register. The LED in the blue box represents the bit to shift to the register. Shift bit shifts to bit 0 to bit 1, bit 1 to bit 2, all the way to bit 7. Bit shifting is triggered by pulsing the clock pin, which is invoked by the clicking clock button. Say, when the shift bit LED is on, and you click the clock button, you will see that bits are shifted, from the shift bit, all the way to the last bit of the register. The clear button invokes clearing of the shift register, which is realized by setting the clear pin of the shift register to low. This experiment will be using the Bluetooth module HC-06 as mean to connect to DumbDisplay Android app. It is possible to bypass the HC-06 setup. But then, in order to connect to DumbDisplay Android app, you will need DumbDisplay Wi-Fi bridge. You may want to watch my previous video bridging Arduino Uno and Android DumbDisplay app, DumbDisplay Wi-Fi bridge. Now, let's see the connections. For HC-06 connections, connect VCC to VBus of Pico. Connect GND to a ground pin of Pico. Connect RX to GP7 of Pico. Connect TX to GP8 of Pico. Note that the Pico's UART1 will be used for communicating with HC-06. For 74LS164N connections, connect VCC to 3.3 volt of Pico. Connect GND to a ground pin of Pico. Connect A to VCC of the shift register itself. Connect B to GP6 of Pico. Connect CK to GP27 of Pico. Connect CLR to GP26 of Pico. Connect QA to QD to GP11 to GP14 of Pico. Connect QE to QH to GP16 to GP19 of Pico. That is it, many wires. Now, let's review the sketch. Line 5 defines the macro Bluetooth. If you do not have HC-06 setup, comment out the line. In such a case, you will need to use DumbDisplay Wi-Fi bridge. Lines 8 to 10 define the pin for the 3 controls of the 8-bit shift register. Shift is the pin to set the bit to shift to the register. Actually, it shifts to bit 0 of the register, which is shifted to bit 1, and bit 1 shifted to bit 2, and so on. Clear is the pin when set to low, clears all 8 bits of the register. Clock is the pin when switched to high from low, performs the shifting of the bits. Lines 15 to 19 declare the DumbDisplay object. Note that this block of code will only be effective if the Bluetooth macro is defined. If the Bluetooth macro is not defined, lines 23 and 24 declare the DumbDisplay object instead. Lines 29 to 36 declare the routine get register pin, to map register bit index to actual pin to use. Note that the register pins are 11, 12, 13, 14, 16, 17, 18, and 19, for the 8 bits of the register respectively. Line 41 declares the shift bit DumbDisplay layer, which is only a single LED. Note that this layer, as well as all other layers, will be created in the setup block. Line 42 declares register DumbDisplay layer, which is a row of 8 LEDs. Line 44 declares clock layer as the clock button. When this button is clicked, bit shifting is triggered once. Line 45 declares clear layer as the clear button. When this button is clicked, all 8 bits of the register will be set to 0. Line 46 declares auto layer as the auto button. When this button is clicked, things will be automatic. Line 49 declares the DumbDisplay feedback handler header, which will be actually declared at the end of the sketch. In the setup block, line 53 sets up serial to 115,200 bulb. That means, if you open serial monitor, you will need to set it to 115,200 bulb. Lines 55 to 57 declare the pin mode of the 3 control pins. Lines 59 to 61 is the loop that sets the pin mode of the 8 register pins. Lines 63 and 64 set the initial state of the clock and the clear control pins. Clock is set to 0 because when the clock pin changes from low to high, that is from 0 to 1, shifting will be triggered once. Clear is set to 1 because when the clear pin is set to high, that is 1, the 8 registered bits will be cleared, that is set to 0. Lines 67 to 90 create and set up the different layers mentioned previously. Lines 93 to 97 auto-pin the different layers in the desired way. After the setup block, line 101 declares the global variable shift bit, which is the value to set the shift bit of the shift register to. In fact, its value not only can be 0 or 1, it can be -1 as well. Please note that the value -1 signifies auto mode. Lines 102 and 103 declares 2 global objects, shift bit value and register value, as 2 helper objects to keep track of the shift bit and the register value actually set and in effect. Lines 106 to 110 declare the routine clock, to pulse the clock pin, in order to trigger shifting. Lines 111 to 115 declare the routine clear, to pulse the clear pin, in order to clear the register bits. Lines 116 to 121 declare the routine set shift bit, which set the shift register shift bit and also turn on or off the corresponding LED on DumbDisplay. Note that the routine uses shift bit value object, to ensure that if set value not changed, no duplicate work will be done. Line 122 starts the declaration of the routine show register. In the routine, lines 123 to 131 first read the register value, 1 bit at a time, from the 8 bits of the register. Lines 132 to 135 show the register read, to both serial and DumbDisplay. Notice that register value object is used to avoid showing the same value multiple times in a row. In the loop block, when it is not in auto mode, line 142 calls set shift bit to set the shift bit. Then line 143 calls show register to show the register value. At last, line 144 calls DD yield, giving a chance to DumbDisplay library to do its work. If it is in auto mode, line 148 declares the local variable shift count, setting it to the initial value 0. The shift count local variable is used to keep track of how many times shifting has happened. Line 149 starts the while loop, which will keep looping as long as shift bit is -1, that is in auto mode. While still in auto mode, line 150 calls show register to show the register value. Line 151 determines the shift bit to use. It will be 1 only if shift count is 0, that is at the beginning of the counting. Line 152 calls set shift bit to set the shift bit. Line 153 delays for 500 milliseconds, using the routine DD delay. Note that using DD delay also provides chances for DumbDisplay library to do its work. Then line 154 calls clock to trigger shifting. Lines 155 to 159 increment the shift count local variable. Note that it checks to make sure the counter only can have values ranging from 0 to 7. Finally, at the end of the sketch, line 164 declares the feedback handler. If it is not in auto mode, and the shift bit button is clicked, simply set the global variable shift bit to 0 or 1, that is the reverse of its old value. If the clock button is clicked, line 174 calls clock to trigger shifting. If the clear button is clicked, line 176 calls clear to clear the register bits. If the auto button is clicked, set the global shift bit variable to -1, that is auto mode, clear the register bits, and set the background of the auto button to hint it is in auto mode. If it is in auto mode, line 183 to 186 reset things in manual mode. That concludes the sketch of this experiment. In order to add more fun to the mix, I will connect 8 LEDs to the 8 output bits of the shift register. To make it more challenging, or easier, I will use the first column of an 8x8 LED matrix for the purpose. The 8x8 LED matrix used has 16 input pins. The way the 16 input pins control the on-off of the 64 LEDs is quite interesting. 8 input pins control the 8 rows, 8 input pins control the 8 columns. Say, to turn on the LED at row 4 column 6, the corresponding row pin and column pin need to complete a circuit. That is, row pin 4 needs be high, and column pin 6 needs be connected to ground. The end result is that the 8 row pins and 8 column pins sort of be able to control the 64 LEDs. It reminds me of the good old game, Battleship. As a result, to use the first column as the LEDs for this experiment is quite straightforward. Just connect the 8 row pins to the 8-bit of the shift register, and connect the first column pin to ground. However, be warned that the pins of the 8x8 LED matrix used are not laid out in the expected manner. Instead, it normally is necessary to refer to a mapping diagram to correctly make the connections. Don't worry, a link to such diagram is shown in the description of this video. As you should have guessed, my next video will be a complete experiment on controlling an 8x8 LED matrix using shift registers. Yes, until then, may God bless you.